Okay, so today we pick up from what we taught last week. So we already know how to calculate the likelihood from this example. So if our observed data is 14, and we can calculate the likelihood we can observe the 14 for each different different pair of the dice. So we all understand this, right? Okay. So in case of for molecular phylogenetics, so we know the data is a sequence we observed, the sequence you get, and the hypothesis is a tree, and also other parameters. Okay. So in the hypothesis, in the previous example, is a pair of dice, but here is a phylogenetic tree, including the topology, the branch length, and also the transition matrix and base frequencies. So we want to find out what the tree can maximize observed data. So that's the basic idea. So that is, given a model of sequence evolution and proposed the tree structure, the likelihood for the null sequence, we can calculate that on the tree structure. So if we can calculate the likelihood, then we can find out which one give us the maximum likelihood. Then that will be the maximum likelihood estimation of the tree. So then here's the question: how to calculate the likelihood given the tree and the data? So you can skip all this text, but we can see here. For example, if we have two sequences, very simple sequence, and the d is a distance, is a divergence length, the divergence between the two sequences. So here we want to calculate the likelihood we observe the G in the sequence 1 and also observe the G in sequence 2. So that should be easy. So this likelihood is, the pi is the frequency, the stationary frequency of G in the population. Okay. So say in the population we saw the G is 1/4. So 25%. So this pi is 25%. We see G here. And this P is the probability transit from this G to the second sequence here. So it depends on the distance. So if you have longer branch between these two sequences, you have a high probability for a change. So the likelihood we see G in sequence 1 and G in sequence 2 is calculated like that. So we have the stationary frequency and also the transition probability as the divergence time. So you all get that? Okay. If you guys follow this. So that's the likelihood we see G in this column for both sequences. We can do that similarly for the second column, okay? So the second column, the likelihood is the pi A, we say A here, and the P from A to G in terms of the distance. So this is the likelihood for these two sites. And the likelihood for we observe the alignment, okay, for both sides, just time them, just multiply them together. So would be this likelihood times that. So that would be the total likelihood for the alignment. Okay. But where is the tree comes to play? So that's just the two sequence. But if we have multiple sequence, the sequence can relate to each other as a tree structure, as we remember from a previous lecture. Okay, so yeah, this is just repeat what I said. You just time the probability, the likelihood for all the sites. But if we put this on a tree structure, okay, so this is tell us how to calculate the P. Okay, so the PAA is calculated as these numbers here. I will explain that in a minute. And for this calculation, we assume the simplest model, the Jukes-Cantor model. So all transition between different nuclei are the same. They're all equals to alpha. So because the transition is, we can fit that as a Poisson distribution. So we can use this function to calculate the change between these two sequences. So for example, so this is pi. For that one, if we see both G in these two sequences, so the stationary probability you see at G is 1/4, but you can also have some other nucleotide change. For example, from A, T, or C, change from A, T, C to G. So that is this part. Okay. So if we see two Gs, so it is 1/4 plus this part. But if we say a change from A to G, so the probability we see A here is 1/4, but the A, we see a G here is 1/4, but the G can also change to other 3 different nucleotides, so we need to minus this. Okay, so this it seems a complicated function, but you can trust me, this has been well resolved and proved. And if we calculate, if we put all this in a tree structure, for example, we have 4 species here. It's unrooted tree. Okay. What we observe is the terminal taxa, these 4 species here. And if we can assume the internal state. Okay. We just for the convenience for right now, we assume the internal state. So we can start from any of these nodes. For example, we can start from this A. So we can calculate the likelihood observed this tree. It is as from this A to this A. So we got the pi A is 1 divided by 4, 1/4, and times this transition probability, as we see in a previous slide. And also times from this A to this one. Okay. So here is the V2 is the branch length. Okay. So the V is the branch length. For A to A, it's also described as this function. And from A to C, it is calculated like this, but branch length, we use V3. And you can explore the whole tree and time all these likelihood together. So this is the likelihood we see we see A, C, A, T in the terminal taxa on this tree. So this is basically how we calculate the likelihood, just like the example we show in the first slide. So we calculated the likelihood for the pair of dice because we know if you have 6 face dice, so for each face you have 1 divided by 6. Okay, so just this is the function how you calculate the likelihood. But for the phylogeny, it looks a little bit complicated than that, but it's essentially is if we can find a way, if we can write down a function, how to calculate the likelihood, given the model. So the model here is a tree, and branch length, and the transition matrix. So as long as we can calculate the likelihood, so we can use the maximum likelihood method to estimate the tree.
So how do you know the
Yes, exactly. So, so your question is how do we know this is A? Could be a C or T or G, right? Okay. So you understand her question? Okay. Exactly. So we don't know. So what do we observe? This is just the next slide right here. Okay. So we don't know what the internal state of this internal node. It could be ATCG. So how to solve that problem? The ancestral state is hidden. Okay. So what we do is we just explore all the possibilities. Okay. So we could have 4 different nucleotides here and 4 different nucleotides here. It will be 4 times 4 would be 16. 16 alternative. So we calculate the likelihood for all these possibilities, and we find the one with maximum likelihood. Okay. So you can see there's a lot of calculation. There's a lot of calculation, but it can be done. So it will be too exhaustive to sum up all of them. But there are some tricks you can do it, because for part of the tree, for example, the first 4 trees, this clade or this part subtree, they're all the same. So we don't have to calculate them multiple times. So we just calculate the likelihood for this part for 1 tree, and next time when we see the same subtree, we don't have to calculate the likelihood again. Okay, so you can also find the similar one here. There's a more slides in the original one. If you check the last week, the PPT from the last week, there's a more slides there. So there's more tricks you can do this more efficiently. But I'm not going to spend more time on that. But you can see because we don't know the hidden state, so we just find an efficient way to explore all the possible possible state for the internal node, and find out the one give you the maximum likelihood. So, okay. So why we want to use maximum likelihood? Because it can incorporate explicitly models of sequence evolution. So it can assume a Jukes-Cantor model or a GTR model. So we know how the underlying evolution rules for those sequence. If you want to say that, but there are 3 challenges. So doing calculate the likelihood. So we already see we need a topology. We need to use a topology, right? So so for example, when we calculate the likelihood here, okay, so we need to use this tree. We need to know the relationship between these 4 taxa. So this is a topology. But not only we will use a topology, we also need the branch length, right? In this function, we also have those branch lengths. So the first challenge is we need use the topology and the branch length in the calculation of the likelihood. But the topology can be tremendous numbers. If you remember from last week, if we have 15 taxa, the possible topology is untractable number. And also the branch length, you will think the branch length can change continuously. So we can stretch these taxa. You have longer branch, and we can push that. You have a shorter branch. So the space of the branch length is also incredible. So that's the first challenge. We need to find the best topology, and the best branch length can give us a maximum likelihood, right? So that's the first challenge. Okay, so we need estimate the branch length and the topology, and also which parameters in the transition matrix we also need to optimize. So in this calculation, So in this calculation, we not only rely on the topology and on the branch length, but we also need this pi. Okay, this is stationary nucleotide frequencies, and we also need so this assume the Jukes-Cantor model. We also need to estimate the alpha, the value of the alpha. So when we calculate the maximum likelihood, when we calculate the likelihood from the tree, so what we need estimate is a branch length, topology, and parameters. So I summarize that in this figure. So that's our data, the sequence you get. So we have an alignment. We all know how to make an alignment from previous lecture. And those are the model, okay? So if we compare the rolling dice example, so that's the 18, the combination of the number. So that is which pair of dice we use, okay? For this phylogeny, so this is the model. So the model includes the topology and branch length, and also the substitution matrix and the base frequencies. So we all see all these parameters for the model. They have a very large parameter space. So the task or the job for the maximum likelihood estimation is we try to find the best tree branch length, the best number for all these parameters, which can give us the maximum likelihood values to observe this data. Right, so you all follow the logic here. So we need to find the best estimation of all these to estimate, to calculate the likelihood, and find that one can give us the best likelihood. Okay, but what we're really interested in is the tree. We don't really care about those substitution metrics or the base frequencies. So when we reconstruct the tree, what we're interested is the topology and branch length. So this we call that nuance parameters. But we still need these to infer the tree. Okay, so how to do that? Like I said, so you can have tremendous different topology and unlimited change of branch length, but for each of them, we can obtain a likelihood by using that function. But how we find the one give us the largest or the maximum likelihood? So there's a one technique to do that called random walking. So this is a metaphor like a robot walking up and down the hills. So I took this from University of Connecticut, their website, just for illustration. So for example, for this guy, you can start this process from a random tree, or you can from a better guess, like we can build a neighbor joining tree or maximum parsimony tree, and use that as a start stage. So say this guy start from here, and standing here means he assume a one particular topology, branch length, and all the other parameters. Okay, and then we can change those. So we can switch the branch. We can stretch the branch length, or we can change the value of the substitution matrix. Okay, we can change those. So let's go back and forth. So for example, first we can take a particular tree and a particular number for all these metrics. We find a likelihood for that robot. Okay, then we can change those. You can change them according to certain rules. Okay, and after that, you calculate the likelihood again. So you will have a new likelihood numbers, right? And for these numbers, it can give you a choice. Can have a choice. So it will calculate the ratio of the new likelihood to the original one. So if the ratio larger than 1, so for these particular algorithms, so if the ratio is larger than 1, means he will go up. Okay, so he can take a step, goes up. Okay. So gradually, so this guy will climb up the hills. Okay. But for it works, it cannot only go one direction. It has to tolerate some steps goes down. Otherwise, so we see this surface. This is a probability surface. Only have one peak here, but sometimes it may have multiple peaks. So, for example, if a suboptimal peaks is here, this guy may stuck in the suboptimal. Okay, so if he cannot go down, if it only goes up, if we have another peak here, this guy goes up on top of that suboptimal, he was stuck there, and he will never find the global optimal, which is better than that one. So he has to take some risk to go down to the here. So that is the choice he makes here. So so if the ratio, so slightly down here, steps are usually accepted. So if the ratio is close to 1, okay, so he can move to a worse likelihood space. But if the ratio is too deep, okay, so this ratio is 0.03, so he will not go to this cliff. Otherwise, he will die. Okay, it's too deep. So in this case, we can make sure this robot can gradually find the global optimal in the likelihood surface. Okay. 那我讲的这些你们都理解吗？有没有问题？你有问题？没听懂？OK。那前面计算这个自然率的计算自然率方法，你们都听懂了吗？计算自然率的话，我们需要这个模型 ，OK， 然后这是我们看到的数据。OK， 那么这个模型里面会包括这个树的这个拓扑结构和这个树枝的长度，还包括这个碱基替换的这个矩阵，还包括它们的平衡状态下的这个叫什么碱基频率。为什么我们需要这些呢？前面这里我给大家看了。就是我们如果计算它的自然率的话，假设这 AACT 是我们看到的4个物种的一个基因的一列上面的数据 ，OK， 那我们要计算我们看到这一列数据的它的自然率怎么计算呢？自然率计算的话，你需要这一个树的结构 ，OK， 然后你还需要每一个树枝的长度，因为这计算的时候还需要这个还需要知道这4种碱基它在这个群体当中的平衡时候的这个碱基的频率。因为这些都是我们这公式当中用到的 ，OK， 这是派这个 A 在这个群体当中的频率。假如你在 A 当中看了25%，那它就是25%。OK， 然后呢，这一部分的计算的时候是需要知道这个树的它的拓扑结构，还需要它的这个树枝的长度，因为这里用的树枝的长度，还需要它的那个这里用的是 Jukes-Kandel 模型，还需要知道 Jukes-Kandel 模型它的阿尔法参数的值，在这个公式当中都用到了。那么也就是这个模型里面的这个3个部分，是我们需要用到来计算你观测到这个序列比例好的序列的自然率的一些参数。OK， 那我们这个 ML 的方法，最大自然率的方法，它的这个 基本的逻辑就是，我可以调整这些数的结构，调整数据结构、数字的长度，调整它的这些碱基替换率，然后调整之后，每次调整之后，你会可以计算出观测到这个数值的一个自然率，对不对？刚才前面公式告诉你了。但每次调整之后，你计算的自然率大小是不一样的。那最大自然率的基本逻辑就是说，你找到这个自然率最大的时候，那么你这一些参数的估计值，就是这个最大自然率的估计值。听懂吧 ？OK， 那这里我们关心的实际上是这个数，这些参数我们不关心，但是你计算的时候需要这些参数。但是前面的问题就是什么呢？那这个数它的那个拓扑结构可以有很多。我们第一节课说了前面那节课说了，如果有15个物种的话，它的那个可能的数就像天文数字一样，你没办法每一种都去试。然后这个树枝的长度也是无限的，你可以把这个树枝长度拉长，可以把它压缩短。那么我们怎么可能把那些无限的空间里面的所有的参数都去试一遍，然后找到哪一个计算出的自然率最大呢？是不可能的，对不对？所以说这个最大自然率的方法，它是一个叫做 heuristic 的方法，它不是 exhaustive 的，你不能把所有的可能都拿来去比，然后找到最大的，这个是做不到的。那我们怎么办呢？那么就用了这个就是 random walking 的方法。那这个就是一个 heuristic 的方法。它是怎么做呢？它是让这小机器人，这是用了一个例子 ，OK， 用了一个例子，让小机器人去爬山。那刚开始的时候，你可以随机的取一个开始的位置，你可以随机的用一个数，或者你用个比较好的开始位。我们可以先用这个 nj 去建一个数 ，Neighbor 建一个数，或者 np 建一个数 ，OK， 这是它开始的位置。那开始的位置这里就是我刚才说了什么意思？开始的位置就是说它这些参数你都取了一个值，你取了一个数，然后这些都取了一个值 ，OK， 所以这个时候你计算出来的这个 likelihood 是在这里，是在1点几在这个位置，所以这是你现在站的地方。那么下面我们就可以把那个把前面那些参数都变一下，你可以把那个数变一下，可以把那个碱基替换的这些概率啊，你可以变一下 ，OK， 你可以随机的变，但是你也可以按照某一些方法，这样效率更高。那变一下之后，你可以重新计算一个自然率。然后你把你新计算这个自然率跟原来这个自然率去比 ，OK， 如果这个比值大于1的话，那你就取你新的这个位置 ，OK。假设我们把这个变了之后，然后一计算大于1，那我现在这个人就走到这里来了 ，OK。走到这里来是什么意思？那这个时候你可能你的那个数是不一样的，你那些参数的值可能都不一样了，对不对？然后如果按照这个情况的话，你就会慢慢就会爬到这个坡的这个顶上，那这里就是你最大自然率的估计值。这个时候，你在这个坡顶上的时候，你那个时候所采用的数，还有树枝的长度，那就是我们的这个最大自然率的这个系统发育式的估计值 ，OK。但这里还有一点问题，就是说，这个最大自然率的这个分布它是只有一个峰的。但是在我们在建这个数的时候，很多情况下它的概率它不是一个峰，可能在这里还有一个小的峰 ，OK。那所以说，如果大于1它就往上走，小于1它就不走，那它很可能就会停滞在这个小的峰这里了。这样的话，你永远找不到这个最大自然率的估计值 ，OK， 永远到不到这个 global maximum。所以这样的话，它还要有一点改动，就是说，它如果小于1。它也不一定说它就不能到那里去，它比方说它可能小于0.9，它就不会到那里去，但是可能大于在0.9以上它都可以走。那这样的话，它如果在这个小的峰这里的话，只要它这个坡不是很陡，它还可以走下去。那这样最后保证它还能够走到这最高的峰这里 ，OK。但是像这个坡比较陡的，像这个坡比较陡，这个悬崖一样的陡坡，它是不会跳下去的 ，OK， 跳下去它会摔死。所以说这是一个技术吧，一个computation 的这个implementation， 它是一个技术，一个 heuristic， 让它能够找到最大自然率的一个方法。我用中文讲了，你们都明白吗 ？OK。模型是指定的，但是模型的参数是需要你估计的。对，因为我们这里是用的 Jukes-Kent 的模型，对吧？我们这里用的 Jukes-Kent 的模型就是 对，大家都是阿尔法，但是阿尔法取什么值呢？对吧？阿尔法从0可以到1，可以取好多值，不止0到1，可以取很多值。那么这个参数也是要估算的。所以这是一个这个 ML 的方法，怎么样去建这个系统树？但是 ML 方法其实可以用在很多很多方面，就是说我们做生物信息学研究，很多这个方面都是用 ML 的方法。所以这个 random walking 这个是计算机算法里面的，不是说用建系统发育树的。就是你如果理解了这个它的这个基本的一个逻辑，那么你以后看到其他的文章或者其他的软件、其他的方法，他说他用 ML 方法去估计的时候，那你就知道它是怎么回事了。OK， 有没有什么问题？计算量就会大很多啊。计算量不会大很多，计算量跟阿尔法是计算量跟阿尔法没有关系。OK， 这个阿尔法就决定了它在这个参数里，在这个 d 这个地方，就是它的那个替换率。这计算量跟它的阿尔法取什么值是没有关系的，但是跟你这个模型的复杂程度有关系。比方说我们 Jukes Candle，OK，Jukes Candle 我们只有一个参数，一个阿尔法。如果你用 GTR 的话，这里有5个参数都不一样，那么它估算的那个计算量就要大很多。OK， 还有计算量还有大很多的就是跟这个数嘛，就是这个数，这数的话，我们这里对吧，只有5个物种。如果你有15物种、50物种，那个计算量就非常非常大。所以这个就是为什么我下面要讲另外一种方法。ML 方法大家都理解了吧？就是说，至少这个基本的道理，基本的道理你们清楚了。对，基本道理就是说，我们观测到数字，我们观测到数据 ，OK， 然后我们有一个模型，那这个模型是我们感兴趣的，在这里这个模型里面包括这个数，对吧？我们感兴趣的。假如你做其他的实验，可能是其他的东西你感兴趣的。然后我们有这个数据之后呢，我们想知道我们感兴趣的这个模型哪一个是最可能的，那这就是 ML 的方法。就是我们根据这个模型，然后来计算出观测的这个数据的一个释然率。首先你要能够写出一个公式，怎么样计算这个释然率？对我们这个建树里面，它的公式就这样的。OK， 你如果能写出一个公式来计算这个释然率的话，然后你找到那个释然率最大的情况下，这个情况下的模型的取的那个值，就是我们最大释然率的估计值。那不管你用在什么研究上面，都是这样的。OK， 但我们这里有一个比较大的问题，就是虽然我们用 MCM 方法，但是空间还是非常非常大。如果物种特别多的时候，它很难保证你能够找到 global optimization， 然后你就有可能找不到最好的结果。OK，so before I introduce you guys about the Bayesian estimation, we can take a look of the difference between likelihood and parsimony. So for example, when we consider this tree, and the nucleotide at the tips of the trees looks like this. Okay. So if we use if we use parsimony under both the parsimony and the likelihood, the nucleotide at ancestor 2 should be A, right? So if we use parsimony, so because all these are A, so here should be an A. If we use a likelihood, it's also should be an A. But the ancestor of the 1 gives rise to lineage for the A and also for C. Okay, so but it also gives rise to G. So what should be the state at the node of 1? So under parsimony, ancestor 1 should be equally well be A, C, or G, right? If you remember, the parsimony maximum parsimony means we have the least number of change to explain the data. So here, if we have A, we will have one change to C and one change to G. Okay. If we have C, if we say it is C here, you also have one change to A, one change to G. So they will all have two changes. So it'll be equal. But on the likelihood, the ancestor is more likely to have been an A than a C or G. Why? So if on the maximum likelihood, say it is more possible to be an A than to C and G, because there is a more opportunity to change on the long branch leading to C than it is on the short branch leading to A. So you guys see that difference? So for the parsimony, it'll be the same. We can either be an A or C or G, so they all have two change. But for the maximum likelihood, because this branch is very short, okay, it's very short, and that two branch is long. So if we put a C here, which means we'll have a change from C to A in this very short branch. It's less likely if we have an A here, it can change from A to C at this longer branch. So you guys see the difference? So the maximum parsimony there's a constant argument between the ML method, between the camp of using ML method and parsimony method, like in 10 years ago, but it's kind of setting down right now. So one merit of the likelihood method is it can explicitly incorporate a model in the estimation. 就是我刚才讲的主要是这个 ML 的方法和这 parsimony 方法的区别。刚才用这个例子，对不对？就在这里面就可以看明白。就是用这个例子的话，这个 node 一这个这个节点，它如果取 A 取 C 还是取 G， 在这个 MP 的方法当中结果是一样的，对不对？因为不管它取 A 还是 C 还是 G， 它都要有两个这个替换。按照 MP 的方法，它是看你的替换的多少的，两个替换是一样的。但如果是用 ML 的方法，它更趋向于这里是 A，OK， 因为这个支长非常短。假如这里取 C 的话，那么 C 到 A 这么短时间要发生一个替换 ，OK， 比这个假如这里取 A 到 C 这么长时间发生一个替换的概率要低，所以说它更容易取 A， 对吧？所以这是 ML 和 MP 的方法的差别。And it's also there's difference between the ML method and distance method. So we can take a look at this. For the likelihood method, it has more power because you can incorporate models, and it's more consistency, robustness. It loses less information because it is character based. For distance method, the advantage is very fast. So if you do a neighbor joining tree, it only takes a few seconds. If you run a maximum likelihood tree, it may take hours or days or months. So that's a major difference. 就是和这个基于这个遗传距离的方法去比较，它用这个 ML 方法都是很好的。唯一的缺点就是计算速度，就是运算的时间比较长。OK， 但现在那个很多这个电脑的技术吧，现在一般的说，你如果做系统发育分析的话，都会用 ML 的方法。这些我就不讲了，我再讲。